Hi, this is Math 1650, and this video is going to be over section 3.2, which is going to be on measures of variation. We had looked in video 3.1 at the measures of center. I do want to mention before we even start in this video that I did find a mistake in the blood pressure measurements. Let me go stat disk. Somehow a couple numbers when I was typing them in ended up in the wrong column, and it wasn't a big mistake. I noticed it when I was starting to make this video the first time. Our mean is actually not 132 or whatever we had, but is 133. I would say 93. A median that didn't get changed at all, 132.5. Our mid-range got changed to 135. And our mode is still going to be 130. Still, there was 4 of them, not 3. I think in the video I said there was 3. But that's the only changes we have are those 2 values. I noticed it as I was making this coming video, and this is why I'm actually restarting this video. Alright, so for the measure of variance, there's going to be a couple different ones we look at. The main one we're going to look at is standard deviation. We will go through a couple methods of how we find the standard deviation by hand with hand calculations, but then we'll get into using stat disk. So make sure you still have that data from before in stat disk, and we'll use that as we go. If you don't have it in, you can always pause the video right before we start doing those problems and add it to it. Alright, so some symbols you will see. S stands for the sample standard deviation. Sigma, which is a Greek S, stands for the population standard deviation. It's very important, especially when we get to chapter 7 and chapter 8, that we know if we have a sample standard deviation or population standard deviation. Okay, range is again the highest value minus the lowest value. It's going to be part of the measure of variance, but it's not the best measure because it's only taking into account outliers. So outliers can easily cause a huge range, even when we don't have a huge variation. The standard deviation, this is probably the most important one, is a measure of the amount of variation in a data set and indicates how close values are to the mean. Okay, and it's very important that we know if we have population or a sample, because within the sample we will divide by n-1 when we do this calculation, and in population we don't divide by n, we just divide it by the population size. The reason for the n-1 is we are estimating the mean within the sample, and so we have to take into account what's called a degree of freedom. Alright, so we will do this formula. We will find the difference between each data value and the mean. We're going to square those differences and then add up all the squares, and then divide by either the population size or the sample size minus 1. Then take the square root at the very end. Okay, before we take the square root, we actually have our variance, but once we take the square root, that gives us the standard deviation. All right, so we're going to do one for a population and then one for a sample by hand. So we're going to go back to the problem with the dice. Here the mean is equal to 3.5. We did that before. I'm not going to go through that calculation again. But what we're going to do is we're going to look at the roll. What you roll is 1, 2, 3, 4, 5, 6. We'll look at the difference between that roll and the mean. So the difference between 1 and 3.5 is 2.5, then 1.5, then 0.5. 4 and 3.5 is difference of 0.5, and then difference of 1.5 and 2.5. Okay, notice I didn't use any negative signs because you can think of it as the absolute value. And then we're going to square this. And so when we square each one, we're going to get 6.25 for 2.5 squared. 1.5 squared is 1.25. 0.5 squared is 0.25. And then 0.25, 2.25, 6.25. Okay, so that's the differences between each data value and the mean squared. Then we add this up and we get 17.5. So that's your sum. That's your numerator there. All right, so now to find the variation, start with that. It's sigma squared is your symbol for it. It's going to be equal to 17.5 over the number of sides on a dice, which is 6. And we get, when we divide that, 2.92. Then when we take the square root, we get our standard deviation, and you get 1.71. Okay, so again, standard deviation, this is your variance or variation. No, I read the first time I said variance. Variance describes the variation. All right. So now we'll look at a sample one. Here we have just 4 values from a sample: 22, 22, 26, and 24. So we have to find the average. So this would be 94 over 4, which is 23.5. And then we look at each of these x values. And if they repeat, we repeat them as well. Find the difference with the mean. So it would be 1.5, 1.5, 2.5, 0.5. Then find that difference squared. So 2.25, 2.25, 6.25, and 0.25. And we add them up, we get 11. And so the variance will be 11 over 3, which is 3.67. And this is your variance. And then the standard deviation, square root of 3.67, which is going to be 1.91. This is your standard deviation. Okay. It's a lot of work just for 4 data values. We're not going to want to do it for 10. We're definitely not going to want to do it for higher than 10. So that is where this will come in to do this a lot quicker. So now again, range. I know I've given the equation, I haven't defined it. So is the difference between the highest and lowest data values. And then the measure of variance is a measure of how much the data values are spread out. So the difference here than the standard deviation is how far they are from the mean, and we take into account whether they're below or above the mean. In this, it's just an idea of how far they spread out in general, and so we square out the negative sign to find this, but that's basically what the meaning is. All right, so now let's look at how we do this on fatness. It's actually the exact same way you may have seen it when we were doing the measures of center. You enter your data in the columns. Hopefully you have your data in already. Select data tab, select export data, select the column, and then you look for range, variance, and standard deviation. All right, so make sure you have McDonald's and Jack in the Box entered. We'll go over that. We'll go back to the beginning. So we have 12 values for each of these. We'll go up to explore data, select McDonald's first, evaluate, and then we'll start with the range 195. Hit something in my hand. 195. For the variance, it's 4081. And we'll go around the variance to data value, so 0.70. And then for the standard deviations right below that, 63.89. Okay, so again, that's the McDonald's. We can look and see the mean, median, and mid-range are all the same that we had before. Jack in the Box. The range is 407. The variance is 16,609.30, and the standard deviation is 128.88. All right. So we have our measures there. Oops. We compare these. We can see that Jack in the Box has a higher variation. The range is higher, the variance is higher, and the standard deviation is almost twice that. So, the McDonald's, their standard deviation is about 1 minute, just over 1 minute. The Jack in the Box, their variation is about just over 2 minutes. So, it can be multiple reasons. You can't find the exact reason without knowing the situation that goes on. But it could be anything from maybe there's not consistency for Jack in the Box, or maybe there were just times that they're a lot busier that got measured, and other times when it wasn't as busy. So now we'll look at the Coshocton Police again. We'll look at the values and find the standard deviation for it. So this was column 3. 46.78 was the mean. Standard deviation was 4.096. Or we can say this is 4.10. Right. We will do more with that a little bit later, but for right now, we'll just keep that as that's how you find the standard deviation for that one. Now the blood pressure one again. This is the one that we had an error. This was column 4. Before I go back, I want to make sure we have 14 data values. So explore data, column 4. Right. So our standard deviation is 9.04. Our variance is 81.8, 81.76, and then our range is 30. Okay. For the customer wait times, when we did these, we saw that the mean and the median and mid-range and even the mode were all the same. And we're going to see that too. If we just look at, I won't go back to the mode again, but we just look at those three, 7.15, 7.2, 7.1, and then for column 6, same numbers. Okay, so for Jefferson, our values for the standard deviation is 0.48. For the variance, it's 0.23, and for the range, it's 1.2. For Providence Bank, the standard deviation is 1.82. The variance is 3.32. The range is 5.8. We can see clearly that the Providence Bank, or the individual lines, had the biggest range and biggest variation, with the spread being bigger as well. Right, so the individual lines have largest variation. That should be an A. All right, so let's look at some other things in this chapter. The range rule of thumb. This is kind of a simple way to estimate it. It's not going to be that great of a method, and you'll see a lot of times it will be very far off. But it is a way that we can use to estimate it. It's just taking the range that you have and dividing it by 4. So for example, we can go through a couple of these. So here, the range for the individual line was 5.8. We can divide that by 4, and we get inch over 4. 5.8 over 4, you get 1.45. We can compare it to what we had. We have about 1.82 for the standard deviation. For the range of 1.2, divide that by 4, and you get about 0.3, which is a little lower. Come up here, the blood pressure. Range over 4 will be 30 over 4, which is about 7.5. Right, again, kind of lower. You know, the speedsters, we can look at this from 59.5 minus the 43.5, which is 16, and do that over 4, we get 4. Right, that's probably the closest one we've seen. All right, so it can be a little bit off, and if we have outliers, then it's going to be extremely off. But it is an estimate that we can use. All right, now more importantly is what we call the empirical rule for bell-shaped distribution. So this goes with the normal distribution. We basically are going to divide this into regions based on standard deviation. Okay, so this is one standard deviation. I'm just going to do STD so it's easy to write. Then this is going to be 2 standard deviations away. And then we're going to have I'll do a different color here. 3 standard deviations away. And this again from the mean, which is right there at 0. Okay. Now, 1 standard deviation away is 68% of the data. Okay, so 68% of the data falls within 1 standard deviation from the mean on either side. Okay. Then 95% of the data falls within 2 standard deviations away. And 99.7% of the data falls within 3 standard deviations from the mean. Okay. Now it's important to know this is consider what's ideal, and there is going to be some variation away from this, but this is what we would expect an ideal normal distribution to look like. We also need to look at, if we were to look at 1 standard deviation below the mean, it's the same as 34% below and 34% above. If we do the 95 to be between 1 and 2 standard deviations above, we're taking into account, let's see, 68% fall in that middle. So 95 minus the 68 is 27. So this is about 13.5%. This little region here is about 13.5%. I'm going to do this. And then if we go farther than that out, we're looking at 99.7 minus the 95 is about 4.7%. And so that would be half of that would be 2.35% here, 2.35% here, and in the last region we have 0.3 left over. So this would be 0.15%, and this would be 0.15%. Alright, so we can space them out or kind of do this geometrically based on these regions now. Alright, so if we have heights of women with a bell-shaped distribution, a mean of 63.6, standard deviation of 2.5, using this empirical rule, what is the approximate percentage of women between 56.1 and 71.1? So mean is 63.6, standard deviation is 2.5. So we're going to do the different intervals. So we'll add and subtract 2.5 once to get the first interval. So we'll be at 61.6 when we subtract 2.5. to 66.1. Then we're going to do it again. We're going to subtract 2.5 from 61.5 and we get 58.6, and add it to 66.1 and we get 68.6, and then do it one more time. We get 56.1 to 71.1. Right, so 3 standard deviations away is that range. That means that our data value should consist of 99.7% of the data values. Right, which means that there may be one outlier, maybe none. It could be all 100%, all within 3 standard deviations. Alright, so before you exit this video, let me just look real quick. I want to see if you have to keep. Okay, we're going to look more at the Coshocton police, the blood pressure. So you want to keep those 2 data sets for when we do the next video. Alright, and so in the next video we'll do 3.3. See you then. Bye.